Well, here are some problems on lenses and optical instruments. Basically, correction of eye defects, telescopes, and one problem on a microscope. The first question talks about reading glasses of what power are needed for a person whose near point is 105 centimeters so that he can read a computer screen at 55 centimeters. Assume a lens eye distance of 1.8 centimeters. Now, this person has a near point 105 centimeters, so he can only read something that is kept 105 centimeters away. But he should be able to read the computer screen, which is 55 centimeters away. Now, he has a defect that is called long sight because his near point has been shifted. So he has to wear convex lenses. And what will the convex lens do? It will produce an image of the computer screen at a distance of 105 centimeters so that the lens in his eye can take it over from that point. So together the image would be produced on the retina. Okay. Now what's the actual distance of the computer screen? 55 minus 1.8. 53.2 centimeters from the eye lens. Okay, and the image must be produced 105 minus 1.8 centimeters away. So now we have the object distance and we have the image distance. And the power of the lens is 1 by f, and the focal length has to be in meters. So using the lens formula and substituting for DO, that's the object distance and the image distance. Now wait, hold on. Why is the image distance negative? Because it's a virtual image. That's an important point. Because the image is virtual, DI is negative. And then calculations show it's 0.91 diopter. Because it's a positive power, it is a convex lens. Also remember that when you calculate, the distances have to be in meters because that's when you will get the power in diopters. Because this definition works only if the focal length is in meters. In this question, you have a person's left eye being corrected by a negative 4.5 diopter lens. It's negative, that means it's a concave lens. And the lens is 2 centimeters from the eye. Is this person's left eye near or far-sighted? From the last question, we can see that to correct far-sightedness, we have to use a convex lens. And since this is negative power, that means it's a concave lens, and this person has nearsightedness. And this B part, what is this person's eyes far point without glasses? Okay. Now, as explained, since the power is negative, it is a concave lens or a diverging lens, and he is nearsighted. He or she is nearsighted. The B part, the far point is the image distance. When the object is at infinity. Now the reason is, for a normal eye, the far point is infinity. But for this person, obviously his far point is not infinity because he cannot see beyond a certain distance. But when he wears those concave lenses, what is going to happen is an object at infinity is going to have its image produced at his far point. And then the eye lens can take it up from there. So that should be clear. When the object is at infinity, the concave lens produces the image at his far point, and then he can see. So to find his far point, you just have to find the image distance for an object at infinity, and which is really easy because DO is infinity and you're looking for DI, and 1 by F is negative 4.5 because that's diopters. So DI is the reciprocal of that, and you get minus 22.2 centimeters. And because the distance of the lens is 2 centimeters, we're going to say the far point should be 24.2 centimeters from the eye, which is 22.2 plus 2. And you're taking the absolute value when you add, okay? Otherwise, you get the wrong answer. Brings us to the next question. A person's right eye can see objects clearly only if they are between 25 centimeters and 78 centimeters. What power of contact lens is required so the objects far away are sharp? And what will be the near point with the lens in place? So two parts here. The objects far away must be clear. That means when the object is at infinity, the contact lens should produce its image at 78 centimeters. So when DO is infinity, DI must be 0.78 meters. And that should be in front of the eye. And again, power is 1 by F is equal to 1 by DO plus 1 by DI. And DI is a negative again because it's a virtual image and it's a concave lens. So now the answer is minus 1.282 diopter. And what will be the near point with the lens in place? So we're looking for the object distance now. And DI is 25 because it's given in the problem. You can only see up to 25. And we already got the focal length. And don't worry about this calculation that I'm doing because you can simply substitute and use a calculator to find the answer. But I'm just doing it this way. Just find DO. DI is negative 0.25, that's in meters, and you have the power and all that. But like I said, you can just take it off from here and put it into the calculator and find DO. That'll be easy. So the answer is 0.37 meter. And then next question, an astronomical telescope has an objective with focal length 75 centimeter and a plus 35 diopter eyepiece. What is the total magnification? Now for a telescope, magnification is the ratio of the focal length of the objective to the focal length of the eyepiece. In fact, negative of that. So, and you know that 1 by FE is nothing but the power of the eyepiece, which is given So it's a direct question. The magnification is going to be 26 times, okay? Magnification is 26 times, and the final negative shows it doesn't matter actually, just know that it's 26 times. And the next question says an astronomical telescope has its two lenses spaced 78 centimeters apart, and the objective lens has a focal length of 75.5. What is the magnification of this telescope? You have to assume a relaxed eye. When the lenses are kept at a distance, and you know that the objective is at one end and the eyepiece is at the other end, and you can change the distances between the two lenses. That's what you do when you are focusing it. And in this case, you see that for a distant object, and when the eye is relaxed as given in the problem, there is a particular formula to find the magnification. Now, first of all, remember that when you say relaxed eye, the final image is at infinity, and therefore the length of the telescope would be the sum of the focal lengths. Okay, so if you have the total length of the telescope, that will be the sum of the focal lengths, because the image produced by the objective must be exactly at the focal point of the eyepiece. That's when it can produce the final image at infinity. And then magnification is minus FO by FE. So now we can substitute for the focal length of the eyepiece from this equation as L minus FO, and the problem is solved. You calculate that, you get minus 30 times. That's it. So just remember, this can be used only if it says it's a relaxed eye. That means the final image is at infinity. Brings us to the next one, and that says, what is the magnifying power of an astronomical telescope using a reflecting mirror whose radius of curvature is 6.4 meter and an eyepiece whose focal length is 2.8 centimeter? Oh, this is like a joke, because if the radius of curvature is given, the focal length is 1/2 of that, so it's 3.2 meter. And then you have the focal length of the eyepiece directly given, so just find the magnification as we've done before. It's 114 times. That's it. Now, next it talks about an astronomical telescope is adjusted for a relaxed eye when the two lenses are 1.25 meter apart. What is the focal length of each lens? Okay, the total magnification is 120 times. Now this is like this problem that we did before. Again, it's a relaxed eye. That means the final image is at infinity. And also it means that the length of the telescope tube must be equal to the sum of the focal lengths. So the distance between the lenses is given as 1.25 meter. And then we know L is F0 plus Fe. What you mean by distance between the lenses here is nothing but the length. Okay? And so you're asked to find the focal length of each lens, so I have to change the subject and make the subject FO. That's what I'm trying to do now. To take FO common. So there is some algebra here. Just look at the steps and follow them carefully. And then finally I have focal length as the subject and substitute the magnification. Just remember, you got to have it as negative. Okay. Length of the tube is 1.25. Put into that, you get 1.24 meter. And so what is Fe? Fe is 0.01 meters. So understand that it's so close. The length, the distance is almost, the distance is actually the sum of the two focal lengths. If you look, the distance between the two lenses, so the length is the sum of these two. Okay, brings us to the last question. This is regarding a microscope. And I want you to understand how a microscope produces an image. And you will have to study this for the exam because it's very important. Let's take a look at how a microscope produces an image. Okay, take a look at this. There are two lenses again. One is the objective, the other is the eyepiece. And the object is kept just outside the focal point of the objective. PQ is the object. And you can see it's kept just outside the focal point of the objective. And then you can find how its image is produced. A parallel ray goes through the focal point. A ray through the optic center just passes through. And finally you have the image at P prime, Q prime, right? That is the image. And since that image is inside the focal point of the eyepiece, the eyepiece is now going to produce a virtual image of that, and that is your final image. So that's how a microscope produces an image. All right? And in this question, you're asked to find the magnification produced by a 0.150 centimeter focal length microscope objective. So that's FO. That is 0.155 centimeter from the object. So that is DO. Now using those two, we can find DI for the objective, and then you can find the magnification of the objective. Right? That's it, because magnification is negative DI by DO. And then to find the overall magnification, just multiply the magnification of the objective and the eyepiece. That's it, and that's how you do it. So DO is 0.155 centimeter, FO 0.150 centimeter. The aim is to find DI. Use the lens equation. It is a convex lens, so the focal length is going to be positive. Make DI the subject and substitute. And when you calculate, you get DI as 4.65 centimeter. Magnification is negative DI by DO, gives you negative 4.65 divided by 0.155. That gives 30 times. That's the answer to A. And for B, total magnification is the product of the individual magnifications. So the product of magnification of the objective and that of the eyepiece. So 30 times 8 is 240 times is the answer. So good luck on the exam. Prepare well and be confident. Thank you.